All right, if everyone take their seat, I'll be getting started here in a second.
You want this open or closed?
You can close one. All right, I'll go ahead and get started. I'm Zach Underwood. I have been doing the networking here at the SouthEast LinuxFest for, this is the 10th year, minus the 2 COVID years. Of course, we didn't meet on site. I live in Spartanburg, South Carolina, about an hour and 10 minutes from here. And my day job right now is as a Linux sysadmin and VMware admin for a credit union here in North Carolina, but also has extensive history of network sysadmin, worked for a wireless ISP, worked for a company that provided managed wireless to multifamily housing. And so I got a pretty extensive history with Linux, IT, working here. MooseFS, it is a distributed file system that allows you to group multiple disks into a single file system tree. It is GPL'd. It was first released in 2008 with the last release this year. It is a scale-out file system. I currently have 114 terabytes, I believe, in the cluster, but it will scale quite large, multiple petabytes. The way to access it is a Fuse, which is file user space file client, and it support. I have it personally working in Debian Ubuntu distributions, but it's available in FreeBSD and all of the Linux distributions. Some of the features it has is it's got a built-in trash system. So out of the box, when you delete a file in MooseFS, it will remove it from the file tree, but not actually delete it from the disk. It will hold the chunks for a period of 24 hours by default. And it supports your traditional file system features, file locking, snapshots, and quotas. I don't use those 3 options, so I can't speak to them very heavily. For my use case, it is running here at Ceph as where all the videos are being recorded. They are being recorded to my Moose cluster. It's my general NAS at home. It's my Plex storage. It's my family photo storage. It's also the backup destination for my Proxmox cluster. There are 4 key services that run these. Most of these can be on a single instance, but it's really, it would be the wrong use case to put all this on a single box, even in separate VMs. It's really designed for multiple nodes. The more nodes and the more drives you throw at it, the better it performs. That's kind of true of all really distributed file systems, but the primary one is the leader, Moose Master Leader, a couple different names. And this is the main leader of the cluster. And it also organizes all of the metadata. In the open source version, unfortunately, it does not support HA. It does support failover, but not HA out of the box. There was a Pro edition. I don't know how much it is. It seems very expensive. The next one is the CGI. Also, it's the web interface, which I'll be showing. It looks a little dated, but it is very functional. The metalogger is, it will save a copy of all the metadata on a schedule back to itself. And in a situation where the leader is gone or never coming back, there is some command line switches you can throw to change a meta logger into a leader. So it does have that failover. And then your chunk servers. Your chunk servers are where your actual hard drives will live. Those are what stores the actual data. So a little between MooseFS, the free open source version, and the pro is HA leader. So again, it is the automatic failover between the master, the multi-master. That is not supported in the free edition. The erasure coding, this is like RAID 5. That is not supported in MooseFS free edition. I'm a little skeptical of erasure coding on distributed file systems. Yes, you do get a lot more effective use of the disks, but it makes the storage of data a lot more complicated, and to me, it seems like it is more error-prone and more risky for your data. The last one is a native Windows client. I kind of wish I had that because I got a few different Windows boxes, but it does not support it. So right now for me, I use one of my Proxmox hosts as a jump box. So it mounts MooseFS on one part of the file system and then shares it out through Samba. And it works good enough for my needs. There's no title, God. So some of the performance characteristics of MooseFS is the more disks you throw at it, the better the performance will get. And this is mostly true with all distributed file systems like Gluster, LinuxFS, Ceph. All of them do better the more nodes, the more disks you can throw at them. Speaking of LinuxFS, LinuxFS is a fork of MooseFS. In the past few years, they have attempted to rewrite from scratch while keeping the same ideas on how a distributed file system should work. I don't know the status of that, and I don't know how actively developed the LinuxFS project is. So metadata is stored in RAM on the leader, and all changes are written in real time to a text log. And then once an hour, that text log is rolled up in as a binary file. That binary file is what gets sent to the metadata logger. So you can change that to send it more often. It's really a toss-off between CPU performance and data integrity. I actually have mine on the default. It seems fine. Every single file on MooseFS is stored in 64 meg chunks. So if it's smaller than 64 megs, then one file equals one chunk. If it is larger than 64 megs, then it will get chunked up into 64 meg sections. Each chunk is then treated independently as far as where it's stored on a disk. So if you have like a 1 gig file, you could potentially have parts of that file stored on every single disk. So when your client goes to access, like read the data, you'll get the performance of reading off of probably every single disk in your cluster. So that's the reason more disks typically equals better performance, because you can spread that load even wider. And then it scales even better with more clients. So single client performance is like here, midpoint. Multiple clients, you'll get more performance the more clients you throw at it, because the requests can be distributed even better. Chunk unique mode. By default, it is treated by disk. So what that basically means is when you have multiple goals, a goal is basically how many copies of that file you want to have. So in my case, I run goals of 2, 3, and 4. So on my goal 2 files, that chunk is stored in 2 hard drives. So if one hard drive dies, I'm still protected. If I have 2 hard drives die simultaneously, I could potentially have data loss for that data that is stored under goal 2. Goal 3, obviously, I can lose 2 drives. And if you have questions, just speak up. You can set the goal per file or per folder recursively. So you can mount the whole thing as one folder. Your MooseFS cluster you can mount as one folder. Then you can have subfolders below it. Like I have important data, I have media, and I have self data. Self data gets 4. It's a goal 4. My Plex data is only a goal 2. Worst case is I lose Plex and I got to re-download a significant amount of data. That's not that end of the world. And then the important data is 3. The higher the goal, the more inefficient use of the disk because you just have that many more copies. But you also potentially get a higher performance because when the client needs to read a file, it has more possible destinations that it can pick from. MooseFS supports the concept of storage classes. And so these are arbitrary classes that you define. So each disk is classified. You can add a label, a classification to each disk. So this is how you would get like your SSD, your NVMe, and your hard drive tiering is by with different classes applied to it. And you basically take a folder in your file system and you say, I want this as the NVMe class. And MooseFS will then move all the chunks for those files onto your NVMe storage. And if you want to automate it, you can just do cron jobs or some type of automation that will reissue the class definition, and then Moose will then take care of rearranging everything for you. It doesn't support by default, it doesn't support the auto tiering. So like you say you want to have all your writes go to the NVMe and then tail off the NVMe onto your hard drive. It doesn't support that. But if you have a use case where you have one folder where you're constantly hammering it, reads and writes, you can put that classification as your NVMe, and so it will only live on NVMe storage. It supports, you can put a node into maintenance mode, and MooseFS will not treat it as offline. Even though it may be actually offline, it will not treat it as offline. And where that comes into importance is if you don't put the node into maintenance mode and it goes offline, it will immediately start to replicate to try to get the goals back up to their goal, basically. And so that can cause a lot of disk I/O and a lot of network I/O. I made the unfortunate mistake of unplugging the wrong Ethernet cable, and I knew I unplugged the wrong Ethernet cable because I suddenly heard all my hard drives spin up to high activity, and it's like crap. Moose, I took off the wrong node because I had put a node in maintenance, and then I unplugged the wrong node. And then replication priorities. It supports setting priorities based on replication type, whether it is a rebalance. So let's say you add a new hard drive. All the data is safe, but you just want data to go onto that new hard drive. You want that to be a lower priority versus if you have a data failure, like a disk failure, you want trying to get the data safe again to take priority. And so there's like 5 different categories that you can classify. Out of the box, it supports pretty well, but it's got a lot of nerd knobs, and we love nerd knobs. Data safety. All of the chunk servers do checksumming on every single chunk read. So every time you read a file, it checksums it. It confirms the header information, the tail information, and then sends that to the client. If it gives a failure, it will immediately find another chunk, mark that bad chunk, and then work on replicating it back to your goal. It will also do loop checks. So it does this loop check also on startup. So when you start a Moose chunk server, it will scan all of the raw disks and look for all the files that it thinks should be there. It confirms they're really there. And then it also periodically performs this, I believe it's once a 24 hours by default. It will do this loop check where it will confirm all the chunks are there. So if you had something like a bit go bad on a chunk, while it's doing this loop check, it will detect that, tell you that the disk is having a problem, and then make the data safe again. So this is the operation for a read process. It starts by asking, the client will start by asking the master, where's my data? Where is it? The master will reply back, you need these chunks, and these chunks are found on these IP addresses, the chunk servers. The client will then request to the chunk server, I need this chunk. And the chunk server will then send that back to the client. And so it can read from potentially every chunk server at the same time. A write operation. This one's a little more complicated. It starts off with client asking the master, where do you want me to write it? Master replying back, first that the master will create the chunks on the chunk servers and then tell the client where to find those chunks. The client will then write that chunk to one chunk server. And now it will write, again, remember it is doing multiple writes for different chunks, but each chunk itself is only written to one chunk server. The chunk server will then take care of replicating it. They do this to minimize client bandwidth. So instead of, if you got a goal 3 and you're writing a 1 gig file, if they didn't do this process, you'd have to write 3 gigs out the network. Where with this, you only write 1 gig out of the network. So it then writes the data to the chunk server, again, replication, then it gets back a success after the chunk server has replicated it around to a minimum of a goal 2. It does not consider data safe unless it has 2 copies. And then if you then have like a goal 3 or 4, the client is not waiting on all of that replication for the 3 and 4 copies. Once it hits 2, it's done. One note I did forget to mention on client uniqueness, or chunk uniqueness. By default, it is by disk. That's not a great system because you could potentially have all copies of a chunk, or all copies of one chunk be on the same physical machine. So if you were doing maintenance on the machine, like reboots or hardware maintenance, you could potentially have files offline. So what I do and what I recommend is going into the uniqueness and changing it by host. And so then it will only put one copy of a chunk on one IP address. And that they also have a concept of racks. So you can put in your rack topology. So if you're running a lot of chunk servers, you can go, I only want one chunk in this entire rack. And that would be useful if, of course, you have spread across multiple racks. So this is the MooseFS web interface. Again, it's not pretty. It looks a little old, but it is functional. One advantage that Chunk has over the other distributed file systems is it's very light on RAM. On the leader, so it has an entire copy of all the metadata, and we're at 1 gig of memory on the master. That's nothing. If you looked at something like Ceph, it's a lot more usage. And then even on, let me pull up one of the storage nodes. So this is a Odroid ARM with 2 gigs of RAM, and there's 200 megs used, and this has an 8 terabyte drive attached to it. So with 8 terabytes of drive, a chunk server is using 200 megs of RAM. With Ceph, Ceph requires a minimum of 1 gig of RAM per disk. Minimum. It's impossible to configure less than that. The interface will not take it. So MooseFS does a lot better with lower RAM boards like we use. Here you can see how many chunks I have at each goal. So obviously my goal 2 stuff, that's mainly media, is gets 600,000 roughly, 660,000 chunks in the goal 2. And so you can see when, like here, I'll just go ahead and show y'all what will happen in a disk failure. I can't remember what the file system or the service name is called. It's different on the different hosts based on whether they're systemd or not. So I just shut down one of the clusters, and you can already instantly see that it is already detected, it went offline, and you can see that there are just shy of 80,000 chunks that now only have 1 copy on the network. And what it is starting to do in another minute or 2 is it's going to start replicating to try to bring especially those only with 1 goal, because it prioritizes the ones with only one available copy, and so it is going to start replicating those across the network to try to get back to that minimum of goal 2. Let me just start this so it doesn't freak out too much. And there we go. And you can see it already started. See these blue right here? That is, now that data is safe, that's how many extra chunks have already been created. So there was 10 chunks already created that were extra. And after a few minutes of stabilization, it will delete those extra chunks. You can see here's like the trash. So we got there's 72 gigs in the trash, and then that will auto age out again in 24 hours by default. And this particular cluster is 116 terabytes, and it is spread over 12 disks. MooseFS does really well with different size disks. So right now I have 8 terabyte and 16 terabyte disks, and it's balancing the free space perfectly on them. They are at most 1% variant between each other. And it likes to balance based on free percent. And the other advantage with Moose over Gluster is you can add disks and nodes one at a time. You don't have to add them in replicate pairs. You can just add one disk, and it will start immediately rebalancing the data to try to balance the free space. And then you can also see how much data is being transferred from each disk in each cluster. And let me switch. You can see that some of the nodes have more than 1 disk, some only have 1 disk. It just depends on what specific hardware. And my cluster is a mix of x86 and ARM cores, and it does fine on ARM. I've not run the master on ARM. My master and backup logger are running as VMs. And then all of the physical disks are nodes, or all the physical disks are on physical hardware. They recommend that the underlying disks be formatted with XFS, and so you can see that there is the actual data, and I'll show you what it looks like on the disk. It's just a bunch of folders and with subfiles. Let's see. Oh, there's a lot in there. So there's the actual chunks. It's just MFSs, and each of them will max out about 64 megs. As far as presenting it on a machine, let me find. I have way too many tabs. My browser looks just the same. It's atrocious. Chrome hates me, and my RAM hates me even more. Let's see, here we go. So that's what it looks like when it's mounted. It looks a lot like NFS. As far as how it's handled. Even the exports page, which I'm not going to show you because there is sensitive information in the exports. The exports is just like NFS. You define the data path, and you define hosts that can reach it, so like subnets, and then you define options. So whether you want it read-only, whether you want to allow root, do you want to map it to a specific user ID? Let's see. Here's the exports. This is what it's shown from the GUI. So you can see my different exports and what it's allowed from. Operations, so you can see what types of operations each client is doing, whether it's doing a writes, reads, lookups. Let's see. Resources. This can give you an idea of how many goals you can achieve with your current hardware. So with my hardware, I can go up to a goal 6. That's because I have 6 hosts. The more hosts you have, the higher your goals can be because I have my uniqueness at the host level. It also has built-in charting, so you can look at deletions. You can look at operations. If you change it over to a, let's see, where was it? You can change it over to a chunk. You can change it over to a chunk server, and in a second, it will load the traffic information and all the statistics for that host. I don't know why it's being slow. Welcome to live demos. Questions? Oh, yes.
Let's talk metadata. The bane of every distributed file system's existence. For a product I work on, we support a hyperconverged storage configuration, and one of the things that has always defeated us for a cluster-based approach is the concept of a separate metadata server as well as multi-master abilities. With Cephs being the benchmark for the worst possible way to do it, how does Moose kind of deal with, you said it doesn't do HA, but how does it deal with the failover, especially when you have a scenario where the failover could happen in a net split kind of manner?
So the way they get around it in I can't speak to the Pro Edition. In the open source edition, they get away with it by having one metadata server. So, and it is the authoritative truth. Because you don't have to worry about a split brain when you only have one brain. And it will write out, it's a one-way write out to the backup logger. And so if in the event of a master failure, you can bring up the backup leader as the master.
Even if there was a split between the two, where they may not...
There's not a split. If they become separated, the logger just doesn't get the latest copy of the metadata.
So if you bring it up manually on your own, that's your own.
Yeah, you have to bring up a backup logger as a leader. It is an entirely manual process. There is no automation there. And that's the way this system is designed, that is to make it a more simpler system, they don't support HA.
Is that just through name resolution, then you point the clients to the new location?
That is what I would do is DNS, and that's how I do it. Is I have an A record that points to the leader. I have not yet had to do a failover, but I have dealt with a lot of disk failures. So my go-to way of getting hard drives is 8 and 10 and 12 terabytes off of eBay. Because MooseFS has been so good to me as far as data integrity, I don't mind buying the absolute cheapest hard drives I can get off of eBay. And beginning of this year, I picked up 8 terabyte drives for $75. Which, when the new price is $180 for an 8 terabyte, yeah, I got a steal. But if I have one fail, okay, I'll just throw it in the pile, slap another one in there, and let Moose figure out how to fix it.
So you said earlier that the chunk size is by default, like our max is 64 megabytes, and it's like literally one file per chunk. Okay.
So that 64 is hard-coded. There is no way to get around that. If a file is smaller than 64 megs, then the chunk on the disk will equal the size of the file. If it is bigger than 64 megs, then the file will get split into multiple chunks. And each chunk is then treated based on the goals.
Okay, so smaller files still. Okay, so it's not like padding out.
It is not padding out. Okay.
Yeah, as long as they weren't 64, it's acceptable.
Yeah.
What about security? Is there, encryption and authentication between client and servers and chunk servers and all that?
I do not know. I don't run security on mine. It's all on the same VLAN. Access, I do have it restricted, so the mount points are restricted by IP address, and that is TCP, so you can't spoof it. I then firewall off so that you can't get to the web interface. Frankly, I run this in my home, so what I've done is sufficient. I think it does support keys, but again, I have not personally configured that. This is sufficient for my needs.
Is the moose named Chuck?
I don't understand.
Chuck shows up a lot in your slides. I think
Oh.
it's supposed to be Chunk.
I am a terrible speller, yes, yes.
Okay, going back to that network split question, I understand there's only one leader, so that's not a problem. But you also said that when you disconnected one of your servers, it started into a rebuild mode.
Yep.
So if you have a network failure, is the portion of the network that's still with the leader suddenly going to go crazy trying to rebuild everything or
Yes.
reach the goals?
Yes, unless you put it in maintenance mode.
So you have to be real quick, get it in maintenance mode.
I mean, so when it reconnects, it will stop the rebalancing. It will stop the recovery once it becomes reconnected. And then, again, it will delete any additional copies that got made to bring it back to the original goals.
Thank you.
Does it have like snapshot support?
Yeah, it does support snapshots. Again, I haven't used it. For my use case, I don't need it. But it is listed as one of the supported features.
And is there like any Kubernetes integration, like a driver for it?
That is where it differs a little bit from like Ceph and the others. It only has the use client. So for my use case, again, I use this for media storage and a NAS and a backup destination for VMs. All of that is on Linux boxes, so I don't have a problem with using the Fuse client. So for my use case, it is sufficient.
I saw on the docs that they recommend at least 2 chunk servers plus the master. And have you found that that's a sufficient minimum? Because they also say, for unclear reasons, you're strongly encouraged to have more chunk servers than just 2. Is it just what you were saying about having more nodes allows you to get better performance and
Yes.
higher possible goals, or is there?
Yeah, that's the primary reason. The absolute smallest to be data safe would be 2 chunk servers and a leader. You can run the leader on one of the chunk servers. I wouldn't, because then if that one box goes down, then you've lost access. Because once the leader goes down, clients disconnect, because they only talk to the leader for metadata.
I've got so many questions, but the first one is I've broken, or my customers have broken, a lot of scale-out file systems. I know the single leader is one of the kind of like enterprisey things that's probably breaking. Any other rough corner cases that you've seen or heard of where this thing just falls apart?
I personally would not use it for VM disks.
Okay.
Again, it doesn't have any form of integration into any hypervisor, and your hypervisors need to be able to run the Fuse client. I think Moose's best is like media files, like in my case, Plex. I get actual on-disk data is something like 35 terabytes of media. And for me, I started off with a ZFS array. And ZFS was too limiting because of the drive size needs to be the same, or you waste disk. Once you fill up a chassis, you can't grow. So for me, having the flexibility to add nodes and to be able to mix disk sizes was a huge benefit for me.
Okay. Next question. You said you've run Samba in front of it. How's that working? Or does this do full ACLs or just?
Yep.
Okay.
Yep. It will support ACLs. Yes.
Okay. And then my last question. You talked about like rack level kind of delegation.
Yep.
Is there any other way to specify affinity? Like, for example, if I want to run this across multiple AZs in the cloud, or
Storage classes.
okay.
That would be.
I couldn't like specify like 4 nodes or like more affinity for like these hosts to say do that and then kind of asynchronously replicate to other.
So each storage class is treated as a cluster. Okay. So if you have a West Coast storage class and an East Coast storage class, then it would treat those separately as different classes.
Would it replicate between those 2 storage classes?
I don't think so.
Okay. That's fine. Thanks.
I don't think so, because the other thing you would potentially have is you have a file, some of the chunks would be on the East Coast, and some chunks would be on the West Coast. And if you have your client on the East Coast, for some of the chunks, you're going to have a lot of latency.
Which is what I'm expecting.
Yeah.
But I'd like to, because if I could do like a 5 level or like a 3, I want to have like all sets of chunks local to my clients on that side, and then it slowly replicate out to the other 2.
I have only used it in the scenario of a home lab. So try it for yourself. You can set up VMs with tiny disks and add those as destinations. All MooseFS wants as a mount point to store disks. It doesn't do like Ceph, where Bluestore Ceph wants the whole disk to control the disk. Moose just wants a mount point.
So when you have the mixed disk sizes and you're talking about doing the copies between nodes, does it get weird with having, where it can't satisfy the split between the two because there's more space on one?
Nope. Because
Or it'll violate that rule?
because it only looks at chunks. So it's only looking at up to a 64 meg chunk. So it can move enough chunks around to satisfy.
So it would disturb the old ones to make room for incoming
Yes.
to rebalance? Okay.
Yes, and now if you had a goal-to with 2 servers and 1 disk each, where one disk is 8 terabytes and the other is 16, you might get some funkiness there. But as you add more disks, it will be able to evenly balance everything out. Because as you saw, I got 12 disks split between 16 and 8 terabytes. And within 1%, it had them all at the same amount of free space.
Thank you.
Well, if that's all, thank y'all for coming.